Hello, my name is Brandon Reznicek, and this is my presentation for Lab 5, modeling the drag force for Felix Baumgartner's jump from the stratosphere. The purpose of this experiment was to create a computer model of the free fall of Felix Baumgartner during the Red Bull Stratus event. Baumgartner jumped from an altitude of over 38 kilometers and surpassed the speed of sound during his descent. Our main focus was to develop an accurate model for the drag force acting on him during the fall. We're interested in seeing how similar our model is to real-world data and determining the cause of any differences we may observe. The main underlying physics principle in this experiment is Newton's second law. Newton's second law tells us that the net force acting on an object is equal to the object's mass times its acceleration. We use this to update the object's velocity. We know that the final velocity equals the initial velocity plus the net force over the mass times the change in time. And we use this velocity to update the object's position. We know that the object's final position is equal to the initial position plus the velocity times the change in time. We also know that the weight force is equal to minus the object's mass times g times the unit vector j hat. We will also be taking into account a drag force in this experiment. We chose a laminar drag force model, which means that the drag force is proportional to the object's speed, because our object is at a very high altitude where air density is lower. A viscous drag force model, which means that the drag force is proportional to the square of the speed, is used at lower altitudes where the air density is higher. The equation we're using for drag force is the drag coefficient b times the speed of the object times the unit vector j hat. For our model, the drag coefficient b changes with position because air density varies with altitude. Air density increases in an exponential manner as altitude decreases because it depends on many factors: altitude, strength of the gravitational force, temperature, humidity, etc. Therefore, we created a function for the drag coefficient. In our program, the drag coefficient b updates in every iteration. The function we created tells us that the final drag coefficient b is equal to the initial drag coefficient b plus 1 over the current altitude times a constant c. As altitude decreases, we want our drag coefficient to increase by slightly more in every iteration. Therefore, we add on the inverse of the altitude times a constant c, which we found by trial and error until our model matched real data. We found that c equals 480. The drag coefficient updates and becomes larger in every iteration of our while loop. Because the altitude is decreasing, it increases by slightly more every time. Let's take a look at some known data from Felix Baumgartner's jump. His initial altitude was 38,969 meters. The mass of Baumgartner plus his suit was 150 kilograms. The time of his descent from the moment he jumped to when he deployed his parachute was 256 seconds. Baumgartner jumped forward, implying a non-zero initial velocity, which we estimated to be about 5 meters per second. At 2,500 meters, he deployed his parachute. The max speed he achieved was 377 meters per second. Let's take a look at the code for our model. We started from a starter code provided to us for Lab 2, falling objects. However, we had to make some important modifications. We start by defining some initial conditions. We set our object's mass equal to 150 kilograms. Our object's initial position is equal to 38,969 meters in the positive y-axis. Our object's initial velocity as negative 5 meters per second in the negative y direction. We set our initial time equal to 0 and our delta t equal to 0.2 seconds. Finally, we started with a drag coefficient equal to 0.0001. Next, we have our calculation loop. We set the loop to stop after our final time of 256 seconds. We define our drag force, our weight force, and our net force, which is the sum of the two. Next, we update the object's velocity and use this to update our object's position. Next, we update t and update our drag coefficient b using the equation that we discussed previously. When we run our program, we can see 3 windows pop up. The first one is a visual representation of our object falling. The yellow arrow represents the weight force, and the blue arrow represents the drag force. The next window is a graph of position versus time for our object. Finally, this last window outputs the time, the speed at that time, and the drag coefficient at that time. We can see that initially the drag force is not very strong, which means that the weight force makes our object accelerate downward until it reaches its terminal velocity. At this point, the drag force is equal to the weight force. However, our drag force keeps increasing as altitude decreases because our drag coefficient is increasing. Therefore, the magnitude of the drag force becomes bigger than the weight force and our object begins to slow down. After about 58 seconds, our object reaches its maximum speed of about 354.9 meters per second. This is lower than the actual speed that Felix Baumgartner reached of 377 meters per second. However, it is a pretty close value and it is more than the speed of sound. After he reaches his maximum velocity around here, we can see that Baumgartner starts slowing down and slows down continuously until the end. We can also see that after 256 seconds, his altitude was about 2,500 meters, which matches the real altitude that he deployed his parachute at. Here we can see the actual position versus time data of Felix Baumgartner's jump. It's important to note that the position is measured in feet in this graph, so we're only comparing the general trend between the two graphs. In this graph, the green circle represents the portion of the curve where Baumgartner was supersonic, and the red line represents the moment he deployed his chute. As we can see, the general trend of our model matches the real observation quite accurately. The main differences are that Baumgartner achieves his maximum velocity earlier, and his maximum velocity was obviously larger. There are a few sources of error in our experiment which are important to discuss. First of all, our model for drag is clearly inaccurate. Our model is oversimplified and does not take into account factors such as temperature or humidity. This being said, the model that we created was fairly accurate, and creating a more complicated model was out of our scope. Second of all, we may have used inaccurate data for the mass, the time of descent, or the initial velocity. The data we obtained online for these values were approximations, and while they may be close, they might not always be perfectly accurate. In conclusion, we created a simplified model of Felix Baumgartner's freefall using Newton's second law to predict our object's motion, only taking into account the weight force and the drag force. We chose a laminar model for the drag force, with a drag coefficient that becomes exponentially larger as the altitude decreases. Our model followed a very similar trend to the real-world data, but was not totally accurate. This is because we used an oversimplified model for drag force.